Hello, everyone, and I hope everyone is having a good day and happy Thursday or Friday for those of you who are watching on Friday. And we're coming to an end of our organic chemistry units, and I know how much fun you've had with naming, but we're actually going to put some of that naming scheme, some of those naming lessons aside. We're going to actually talk about probably the most popular part of organic chemistry, the actual organic reactions. As I said in the beginning of this unit, that the cool thing about organic chemistry is because of what carbon can do and how large the carbon or organic molecules can be, there are tens of thousands of organic molecules, and they do everything, right? And really, for organic chemists, one of the biggest skills, one of the biggest challenges they have is making specific compounds, making specific types of molecules, right? So today, we're going to start talking about special organic reactions. And the reason they're so special is because they have everything to do with our functional groups. And to start with, we're going to have what is called the halogen addition reaction. Where we are literally adding a halogen to some sort of organic molecule. Now, hopefully you remember that halogens are group 17s, and group 17s are all part of our diatomic molecules, our Hofbrinkel. They all exist as diatomics. So a great example of a halogenation addition reaction is if we were to take chlorine, Cl2, and we were to add it to ethene. And literally what's going to happen is that the double bond is going to be broken up, and we're going to create this halocarbon. And we can tell this is a halocarbon or a halide because, as we see, it has two functional groups, or two of these halides. So as long as it has one, it's a halocarbon. So for this, we have a halogen plus, in this specific case, we have an alkene. And this creates a halide or a halocarbon. Now, why is this so important to us? Why do we care about this reaction so much? Well, as it turns out, the halide uses are, and these are just some, for example, solvents, pesticides, adhesives, lubricants. I think that's funny because a lubricant and an adhesive are literally opposite. Plastics and electrical insulation, just to name a few. These halides have so many different uses, but we have to be careful because we only want to add halides and specific halides to specific parts of a molecule. Now you will notice that for the addition reaction up here, we added where there was a double bond. The thing about addition reactions are that they won't work for alkanes. Why not? Well, think about it. An alkane is all single bonds. There's no extra place to put these. Alkanes, as it turns out, are something that we call a saturated hydrocarbon. And you probably heard this term before. And you've even heard it in terms of organic molecules. Saturated fat, polyunsaturated fat, right? Saturated oils, we've also talked about the term saturation in terms of solutions. This is a little bit different for solutions because the solution is all about solvent and solute. Saturation has to do with that. Organic chemistry, no water, right? So what is saturation? Well, a saturated hydrocarbon has to do with how many hydrogens are on our hydrocarbon. And saturated hydrocarbons have the max number of single bonds. All right. So alkenes and alkynes are unsaturated. So the only ones that are saturated are alkanes. Right. Now, it is possible to add, it is possible to turn an alkane into a halide. It's just a bit of a different reaction. It's called a substitution reaction. And what we're going to have is we might have something like HCl plus our friend ethane. And what that's going to turn into is sorry, just H2. So notice how with the substitution reaction, instead of just adding to a chain, we are literally substituting one element for another. And those are the two ways that we can make halides. Talking about commercial uses, there's another very, very special functional group that we use in commercials, and those are esters. Esters are used to make all of those artificial fun smells, all of your fruit smells. Anytime you smell something that smells like banana or grape or strawberry or apple or peanut butter or freshly mowed lawn, that all has to do with specific different esters. And as you know, smell is such a strong sense. It's strongly linked to memory. Smell can cause us to feel really good, feel really bad, feel really sick, feel really itchy, all the above, right? So it's really important for chemists to be able to customize different esters. And we have our own special type of reaction called esterification. And the general formula of the esterification is ROH, which is an alcohol, plus, we're going to call that R prime to C, double bonded O, OH. Here's our organic acid. So when you add an alcohol and organic acid, you end up with an ester, but in a very special way. You're going to have, and I want you to note where the R is and the R prime is. You're going to have R to O to C bonded O to R. And here's our ester. Note what happened is that the alcohol gave off a hydrogen and the organic acid gave off an OH. In fact, this also has water. Right? So this is very special because two different sets of alcohol and organic acids will give you different esters. For example, let's look at an ester and let's work backwards. Let's deconstruct it. So an ester is this functional group of R, O, C double bonded O to R. So let's do C to C to C. Let's double bond this O to O to C to C. Right? So let's deconstruct this. We know that this is an ester, and we know this ester came from an alcohol and an organic acid. And the trick here, if we look up here, we notice that this C double bonded O and the next C that it's connected to, that's always coming from the organic acid. So I'm going to look here and I'm going to see this C double bonded O to C. That's my organic acid. And I see that inside of my organic acid, there's going to be 1, 2, 3 carbons. So we can break that part up. We can kind of break it up here. Not completely, but break it up into my organic acid is C to C to C, double bonded O to O, H. The other is my alcohol, and I can see that in my alcohol, there are 2 carbons. So it's going to be a 2-carbon alcohol, OH. Right? So if you combine these two, you create that ester. And that's how we do esterification. We'll do more practice in class, but thank you so much for watching, and I hope to see everyone soon. Bye, y'all.